Hello and welcome to another geometry read-along. Today we are finishing off Chapter 3 with Section 3.5, Volume. Here's our applied problem to get us thinking. At a steel mill, a thick slab of steel 1 meter by 1 meter by 15 centimeters will be rolled into a long strip 1 meter wide and 0.5 centimeters thick. How long will the rolled strip be? So it's going to stay 1 meter wide, but they're going to lengthen it in one dimension by making it thinner and thinner, of course losing no actual steel in the process. So keep that in the back of your mind. Volume itself is the three-dimensional analog of area. To find the volume of a shape, we must designate a unit cube. Then we must determine how many unit cubes completely fill a given three-dimensional space. Okay? So this is similar to what we did with area as a buildup of defining length. And area was length times length. Now we create the cubic unit as seen in the figure. So the following postulate for volume is analogous for the area postulate. And remember, a postulate is something, like a definition. It's something we're going to have to accept as true and build off on that further. It says, for every polyhedron and unit cube, there is a real number that gives the number of unit cubes and partial units of cubes that exactly fill the region enclosed by the polyhedron. Can I stretch it? There we go. The volume of a region enclosed by a polyhedron is the sum of the volumes of the smaller regions into which the region can be subdivided. So again, very similar to what we said with area. Any enclosed space can be counted as the number of unit spaces inside it, as well as the enclosure is the sum of its parts. The real number described in postulate 3.4, right, that number of given cubes, is called the volume of the region enclosed by the polyhedron. All right, so if you want your definition of volume, you will need to use this portion of the postulate. Now, for the sake of simplicity, we usually say the volume of the polyhedron to mean the volume of the region enclosed by the polyhedron. The next example shows how to find the volume of a right rectangular prism. Okay? And again, this is similar to area. Technically speaking, this rectangle is only the line around that perimeter. Its area then is the shaded space inside. So if you want to count the whole thing, you're talking about the rectangular region. Same in three dimensions. A polyhedral region is the volume. But it's easier just to call it the polyhedron itself. So for example, using a unit cube of 1 centimeter by 1 centimeter by 1 centimeter, find the volume of a right rectangular prism 3 centimeters by 4 centimeters by 2 centimeters by counting the number of unit cubes that will fill the prism exactly. There's our image of such a rectangular prism. So as we can see in figure 338, the prism would hold 2 layers of cubes that have dimensions 3 by 4, 3 across, 4 deep. Because there are 3 times 4, 12 cubes in each layer, there are 3 times 4 times 2, or 24 unit cubes in all. Thus, the volume is 24 centimeters cubed. Notice now we are dealing with a three-dimensional measure. Our units are to the power of 3. We may view this result as the product of the area of the base of the prism, 3 by 4, and its height, 2 centimeters. So, what is the volume of a prism in general? As in the case of finding the area of a rectangle, we can find the volume of a prism having real number dimensions using the technique from example 325. And that gives us this definition here. The volume of a prism is the product of the area of its base and its height. So the area of the base, if that is a rectangular base, it's the area of the rectangle. If that is a pentagonal base, as we have here, you must find that first, multiply by the height of the prism, which is always going to be distance between two parallel faces, the bases of the prism. All right? So make sure you have that definition in your notes. There we go. All right, the following two results are immediate consequences of this definition of volume. So we get kind of shortcuts thereof, right? Generally, this is any prism, and thus we can say the volume of a right rectangular prism is the product of its length, width, and height, because the volume of that base face is the length times the width. Right? So we can apply that shortcut there, have that theorem handy as well. And its corollary, okay, we'll get to corollary in a moment. The corollary, the volume of a cube. And you can see this as yet another even shorter shortcut. If you're dealing with a cube, then the volume is the cube of the length of its side, right? Because all sides are congruent here. And so a special note there that a corollary is a theorem that is a direct result or special case of a preceding theorem. Okay? Direct result or a special case. They go together. One automatically gives you the other. In this case, the cube is a special type of a right rectangular prism. So we call it a corollary instead of a new separate theorem. Now, how about volume of a pyramid? That's a little tougher to visualize. We may infer the volume of a pyramid from figure 339, where three pyramids identical to the one on the left are shown to be filling a right prism completely. So notice in this pyramid that apex point is not centered above the base as we usually see it. It is shifted over to the side such that we actually have a right angle here on that front face, and this back going face here, this is also a right angle there. So that when you take three of these, flip and turn them around, this right angle can be this corner, right, matches with that corner. This is a second of those pyramids, and then this back corner is a third of this same pyramid. Now we get these three vertices, or three of the vertices of our right prism. And you've got the other three where the sides meet up. So even though figure 339 pictures a square pyramid, the ratio of three pyramids to one prism holds in general. That is, the volume of a pyramid is 1/3 the volume of the corresponding prism determined by the base and height of the pyramid. Right? So that specific case helps you visualize it, but from very careful measurement and extrapolation, we can determine this holds for any type of pyramid, even one with a funny pentagonal base such as this. So here is our next theorem for the volume of a pyramid, corresponding formula to add to your notes there. 1/3 area of the base times the height. Right? Now let's try an example of that here in example 26. Find the volumes of the polyhedra with dimensions shown in figure 340A and B. A right rectangular prism with dimensions shown, and a right square pyramid with dimensions shown. Notice that they are giving the slant height of the pyramid, not the true height of the pyramid. So how do we deal with the prism? Volume of a right rectangular prism, length times width times height. So we'll take 7.2 times 9.6 times 5.3 or a total of 366.336 centimeters cubed. Now for the pyramid, the slant height is 13 inches. The distance from the center of the base to an edge is 1/2, 24 inches, or 12 inches, see 340C. So if you look in here, what they have done is they have drawn in a line segment from the apex of the pyramid down perpendicular to the square base. And since this is a square pyramid, that line will be perfectly in center. So if we added an additional segment that is a right angle to that front edge, this would also be 12 inches long. And notice that this one comes in and is perpendicular to that edge of the pyramid. So we can be certain that this is all squared up, and half from the corner in to the center of the side, and half up from here gets us to the center point. So it's 12 inches away from the corner to the center. And thus the height, h, satisfies the equation h squared plus 12 squared equals 13 squared. You might recognize that as Pythagorean's theorem, because look what we have now created inside the pyramid. This is a right triangle. And so we can use the Pythagorean theorem. 12 and 13, that is in fact a Pythagorean triple. So we know h must be 5 inches. So the true height of the pyramid is 5 inches. The volume then is given by 1/3 area of the base times height. That base is a square, so its area is 24 inches. The length of the side squared times 1/3 times 5 inches gives us a total of 960 inches cubed. Now, cylinders and cones, just like with surface area, we can develop the formulas for cylinders and cones out of prisms and pyramids. That's exactly what I said. We obtain the formulas for the volumes of cylinders and cones in a manner similar to that used to derive the formulas for their surface area. I really ought to just read the book first, then add my comments, or I'll be repeating myself. In the case of the circular cylinder with a base of radius r, A represents the area of the base, which, being a circle, is pi r squared. The height of the cylinder is represented by h. In figure 341 suggests the following theorems. Extrapolating, just like we did with the surface area, take from a square prism out to a decagon prism, all the way out to a cylinder. You can see that transition of adding more and more sides to approach an infinite number of sides in the circle. Same with pyramid, more sides of a pyramid all the way out to a cone. And so we have then theorem 319, the volume of a right circular cylinder is the product of the area of its base and its height, just like with the prism. However, we know the area of its base will always be pi r squared because a cylinder always has a circular base, whereas a prism could have any polygon for its base. We can't go generalize quite as far. And similarly, volume of a right circular cone is 1/3 the product of the area of its base and its height, which is 1/3 pi r squared times h. I'm sure you've added those two theorems and their formula to your notes. All right, let's put it into practice with example 27. Find the volumes of the right circular cylinder and right circular cone with dimensions given in 342. So here we have a cylinder, diameter 10 feet, height of 12 feet, and a cone whose radius is 6 centimeters and slant height is 10 centimeters. For the cylinder, direct application, pi r squared h. We know r, half the diameter, 5. H is 12 for a total of 300 pi feet cubed. And for the cone, 1/3 pi r squared h. We know the r is 6. That's given. We don't know h, but once again, a right triangle presents itself And we can use, oh, what happened there? We'll just pretend that was a triangle all along. We can use Pythagorean theorem to find the height there. So we've put it in all in one formula. Just do it as one full step square root of 10 squared minus 6 squared, which, if you notice, this is a scale, a doubling of a Pythagorean triple. This is a 3, 4, 5 triangle, so that other side must be 8. So 1/3 times 6 squared times 8 gives us 96 pi centimeters cubed. And although we gave formulas for the volumes of right prisms, pyramids, cylinders, and cones, the same formula holds for similar oblique shapes. Write that down. That is an important thing to remember. Same formula even for the oblique shapes. And if you don't remember the oblique shapes, that's when we have something that is off center. I want a pointy bit, right? Okay, you could have some kind of cone like this, as long as you can draw a height down to the plane of its base. So your height is truly perpendicular from that surface. You can use that to find the true volume, even of a slanty cone or pyramid or prism or cylinder. Now, how about a sphere? We stated in section 3.4 that Archimedes observed that both the surface area and volume of a sphere are 2/3 of the respective surface area and volume of the smallest right circular cylinder containing the sphere. Okay? Here's a picture to remind you of that. Take the smallest possible can that can just barely fit around the ball. So imagine a tennis ball tube that only holds one tennis ball. The sphere has radius r, so the base of the cylinder has radius r, and the height of the cylinder is 2r. Therefore, the volume of the cylinder is area of its base times height, pi r squared times 2r, for a total of 2 pi r cubed. And then the volume of the sphere of radius r can be found as 2/3 of that. So 2/3 times 2 pi r cubed gives us 4/3 pi r cubed. In summary, Theorem 321 tells us the volume of a sphere is 4/3 pi times the cube of its radius. Right in there. And I think I screwed up this rectangle. There we go. All right, let's try an example. Find the radius of a sphere for which the surface area and volume are the same number. Ooh, a little tricky there. Let's set up an equation. Let r be the radius of the sphere, then 4 pi r squared, the surface area, equals 4/3 pi r cubed. Now we solve for r. 4 pi r squared equals 4/3 pi r cubed. We're going to multiply both sides by 3 to get rid of that denominator. So we've got 12 and 4 over here now. And the proper way to solve this is to subtract 4 pi r cubed from both sides. Or rather, I think they've reversed this. Subtract 12 pi r squared from both sides and then rewrote the equation with them on the other side. Same thing there. And then factor out those quantities of r squared. Do not divide both sides by r squared here. Okay? You might accidentally be dividing by 0, so don't do that. But now we're factored 4 pi r squared and left with r minus 3, all equal to 0. Therefore, either the radius equals 0, and I think you can think of that one yourself. If we had shrunk it down to nothingness, well, they'd have no surface area and no volume. 0 equals 0. That's the simplest case, using the zero product property between these two factors. Or r minus 3 is equal to 0, and thus a positive 3 for r will be a solution. So r equals 0 produces a sphere consisting of a single point. The real answer is r equals 3. As a check, a sphere of radius 3 will have a surface area 4 pi times 3 squared, or 36 pi, and the volume will be 4/3 pi times 3 cubed, which is also 36 pi. Of course, the units are square units for the surface area and cubic units for the volume. So perhaps we ought to have started with some form of absolute value identifier here. Right? Ignore the units. All right, now the moment we've all been waiting for. The following table summarizes the surface area and volume formulas we have studied. Connections formed by observing the similarities and differences in the various formulas will help you remember them more easily. I've pointed out a lot of those connections throughout the readings in these videos, but go ahead and now add this table to your notes, even if you've already written down all the other formulas separately. Put them all together in one place for easy reference and ease of study, and particularly comparison, so you can better understand how each of them is built and rely less on pure memorization. Now, what about dimensional analysis? How do we convert units of volume? In section 3.1, we use dimensional analysis to convert units of area measure. The next example shows how we can use dimensional analysis to convert units of volume measure. Okay. So in this example, we are going to convert the volume of dirt that must be removed from a 200-foot-long trench with its cross-section dimensions shown in figure 344. Find the volume in cubic inches first, then convert to cubic yards. And any of you who have done any landscaping will know a lot of dirt, gravel, and mulch and such is sold in cubic yards. So our trench, let me get a solution in figure on the screen there. The trench in figure 44 is a right prism with a base in the shape of a trapezoid, and the height equal to the length of the trench, namely 200 feet. Okay, we were told how long it is that way, which 12 inches per foot is 2,400 inches. And thus we have volume, area of the base times that height. The base is a trapezoid, so we're going to use 1/2 height times sum of the bases. So in this case, height of the trapezoid is 50. 66 and 54 are the two bases. Please do not confuse height of the trapezoid with height of the prism. Two different heights there. Okay? And then all that gives us area of the base trapezoid times the height of the whole prism for a grand total of 7,200,000 cubic inches. To convert from cubic inches to cubic feet, we use the fact that 1 foot cubed equals 1 foot times 1 foot times 1 foot, and convert each foot into inches, which is 12 inches, so we're replacing each factor with its inch equivalent, so 12 times 12 times 12, for a grand factor of 1,728 cubic inches. Hence, the volume is 7,200,000 inches cubed. Set that over 1, multiply by 1 foot cubed over 1,728 inches cubed, so that the cubic inches reduce, cancel out. And much simpler, from cubic feet to cubic yards. 1 yard is 3 feet, so 1 cubic yard is 3 times 3 times 3, or 27 cubic feet. Now the cubic feet's reduced, we're left only with yards cubed, for a total of about 154 cubic yards. So that is approximately how much dirt will be removed from the trench. In that previous example, we calculated the volume first and then performed the conversion. However, we could have converted to yards first and then found the volume in cubic yards. I tend to stick to leaving the conversion for later. I would go in this order, mostly because looking at these numbers, I don't feel, especially with that 50, going with 12s and 3s, right? These will be some fractions or decimals of yards, and we want to try to preserve accuracy and stick with whole numbers where we can. All right, so how about that slab of steel from the start of the section? The volume of the initial slab in cubic meters would have to be, it's a rectangular prism, so length times width times height, or 1 meter times 1 meter times 15 centimeters with metric that's much easier to convert there to 0.15 meters for a total of 0.15 cubic meters. Because the volume of the new longer strip must also be 0.15 cubic meters, we didn't lose any steel, we can find the length L of the new strip. So we'll set our known volume, our known width, our new thickness, and solve for the new length. So we'll just divide everything by the 1 meter and the 0.005 meters over there for a final length of 30 meters. So the new strip will be 30 meters long. And a bit of geometry around us. The sphere is one of the most commonly occurring shapes in nature. Frog eggs, tomatoes, oranges, the earth itself, the moon are a few examples. The regular occurrence of the spherical shape is not coincidental. One explanation for the frequency of the sphere's appearance is that for a given surface area, the sphere encloses the greatest volume. Write that down. For a given surface area, the sphere encloses the greatest volume. In other words, a sphere region requires the least amount of natural material to surround a given volume. So if you're trying to conserve resources, as most biological entities are wont to do, you want to enclose your egg requiring as little pieces to collect from the environment as possible, the spherical shape is the way to go. Now, since this is the end of the chapter, we've got one more thing to address after the exercises there. We have the solution to the chapter's initial problem. If you recall, we were presented with this shape of, say, a board with 3 holes cut out of it. Right? And we wanted to create one object that could fit through each of those holes and fill them entirely. So it must look like it fills the triangular hole. Right? Imagine a plug that fills that hole perfectly and also fills a square hole and fills a circular hole. How do we do this? Well, start with a cylinder whose base has diameter d, which is also the size of the length, the size of the square, and whose height is d, so it will pass through the square and the circle exactly. So you can imagine this cylinder from my side view as I'm looking at it. Here is a square d times d, and if I look down from the top, it's of course a circle diameter d, of course it passes through that hole. We will modify a model of this cylinder to get a shape with a triangular cross section, because we still need to get this third hole. We do that by slicing it. If we slice the cylinder along the heavy lines in figure 34b, so across here, okay, and in 3 dimensions that slice measures all the way back through the cylinder, the resulting model will pass through the triangular hole exactly. So across this way, front to back, it is still that same side. And if I was to rotate this 90 degrees, you would spin it around and you would still see the full width across the top, full width across the bottom. It would still be that full square. But from this direction, now we've got a cross section of a triangle. Figure C shows the resulting model that will pass through all 3 holes exactly. It's a little tough to visualize. This is a 3D object, only 2D pictures. Hey, if you would like some additional problems where using a model is a useful strategy, and particularly a physical model, if you have pencil and paper and tape and glue or modeling clay or pipe cleaner, something to build with, this can be very helpful to help you solve these problems. Go ahead and pause and read through those there. The thing I would like to share with you before we go, there's also a few other writing tasks. You can pause and read those at your leisure. But I would like to end with this. A people in geometry. Pythagoras, right? The one whose super useful theorem we've been using this whole time, was a Greek mathematician who founded a mystical school in southern Italy. The members of the school, known as Pythagoreans, were a brotherhood with secret religious rites. Their motto was, "All is number." They studied the properties of numbers, believing that whole numbers were the basis of the structure of the universe. The Pythagoreans were the first to discover irrational numbers, numbers that cannot be expressed as the quotient of two whole numbers. This discovery was deeply disturbing for the Pythagoreans, for it invalidated some of their mathematical proofs and challenged the assumption that whole numbers were the ultimate reality. Of course, Pythagoras is most famous for the theorem named after him. Although he likely did not discover the Pythagorean theorem, he may have been the first to prove it, at least at the same rigorous level of proof that we accept here today. But that is going to do it for the chapter. Thank you very much for following along. So long, farewell, enjoy the rest of your day.